Hello everybody and very welcome to this video lecture. My name is Dr. Lucas du Plessis. I'm a senior lecturer in the Department of Mechanical and Aeronautical Engineering at the University of Pretoria, and this lecture is for the MOW or Manufacturing and Design class of 2023. In the last lecture there was a question that I wasn't quite sure on how to answer, and I promised that I would get back to the class with an answer. The question related to hobbing of gears, and specifically, is it possible to create a spur gear using hobbing? So this question originated from the slide that I showed in the last lecture of figure 1319 in Shigley's Mechanical Engineering Design, and it shows the hobbing of a worm gear. Okay, the worm gear, how do we know that it's a worm gear? It's the fact that this gear has a round profile that you can see here where my hand is waving. Okay, and I've located another nice image from the internet. This shows the hobbing of a small worm gear, and here also you can see that the gear is actually round, and that's a result of the hobbing cutter that is also round. Okay, and what I've indicated here with these arrows is obviously the hobbing cutter will rotate, and as it engages with the gear blank, this gear will also then rotate as the individual gears or spaces between the adjacent gear teeth gets cut. Right. So now the question, how can hobbing be used then to cut spur gears? Okay. And I've also shown in the previous lecture, I've referred the students to this website. They've got some nice information and nice videos that show how gears are manufactured. So I did a bit of additional research on the internet, and I got hold of this image here that clearly shows all the rotations and movements involved in hobbing of a spur gear. So the gear blank also rotates as the hobbing cutter rotates, and the hobbing cutter is also, there's an axial feed, so in this direction, to ensure that the resulting gear has parallel teeth, not the half round profile of the worm gear. Okay, and I just wanted to also clarify that the hobbing cutter resembles a screw. Okay, so as it rotates, it actually forces the blank also to rotate. Well, yeah, it forces the blank to rotate, or it engages subsequent teeth, and it cuts the complete gear. Okay, and there's a nice video that I would like to show you that actually shows this. Okay, so here you can see the hobbing cutter, a lot of liquids, a lot of cooling fluid. This is the gear blank, and we are now going to cut, or the people in the video are going to cut a spur gear. Okay, so it starts engaging with the gear blank, and you will notice that the hobbing cutter then moves downwards. But note the rotation. A lot of heat gets generated. That's why the cutting fluid is actually creating smoke. Okay, and there you can now clearly see the parallel teeth of the spur gear, and the hobbing cutter is now at the bottom of the gear blank. Right, so there was another question on gear burnishing. That I was also not sure about, and I would like to answer that question. So we said that for very accurate gears, we can apply shaving or burnishing to get the gear profiles very accurate. And the question was, is burnishing then a material removal process? And I thought initially it was, because it was grouped with shaving. Shaving is indeed a material removal process, but burnishing is not. And this last bullet point clarifies that. Burnishing is a method of polishing the surface of a component through compression as opposed to material removal. So it's very much similar to the rolling of gears, which is a cold forming process. The difference is for burnishing, it's a finishing process. So the gear teeth may be formed with another process, and then the gear will be placed in the burnishing machine to do that final compression and forming of the teeth, and then simultaneously also resulting in a very smooth teeth profile. Okay, so those were the questions that resulted from the last lecture. So now today's lecture is then about gears mounting, the mounting of gears on shafts, and with this last content we will then end the content on gears, which is taken from Shigley's chapter 13. Alright, so gears can be mounted on shafts in the following ways, and this is not an exhaustive list, it's not complete, but for the purposes of mow217, for general purposes, I think it is adequate. Okay, we can manufacture the gear and the shaft from the same piece of material. The gear can also be welded onto the shaft. The gear can be clamped. Okay, we can use keyways in the shaft and in the gear, and then we can also employ or apply a non-round shape of the hole in the gear and the shaft. A spring pin or a dowel pin is also an option, and then lastly a grub screw. And we will quickly look at all these mounting techniques. Okay, as a matter of fact, looking at the first one, we already considered rolling, cold forming or rolling of gears from a piece of material, and here you can see the shaft and the gear blank is obviously the same piece of material. These tooling then gets pushed into the raw material to result in a gear. Okay, so we've already watched this YouTube video where this rolling process is actually clearly shown. And just referring back to that video, so the rolling actually happens in both directions, clockwise and counterclockwise. It is obviously to then shape the gear teeth on both sides of the flank. Okay, so what are the properties? Why would we consider a gear rolling? Well, we already mentioned that it results in a very high strength gear teeth, as well as connection between the gear and the shaft. Okay, so the fact that the material is cold worked improves its mechanical properties, so it makes the gear teeth very strong. Plus the fact that we obviously have a very strong connection also between the gear and the shaft, as a result of the cold working. It's a backlash-free connection between the gear and the shaft. Backlash between the two adjacent gears will always be there. Okay, that we already discussed in detail in a previous lecture, but we can, by doing cold or by manufacturing the gear and shaft from the same material, avoid backlash between the gear and the shaft. Okay, you will notice later on that some connection techniques results in a little bit, well, in backlash between the gear and the shaft. But this specific technique, rolling or manufacturing the gear and shaft from the same material, avoids that backlash. We get very high accuracy gear teeth. We also mentioned that, and this is obviously now a result of how good the quality of your tooling, and this obviously then results in high costs. You can imagine these tools don't come cheap, and especially if you want them very accurate, it must be a high quality material, and it will be hardened and ground to a very good accuracy, because the accuracy of your tooling obviously has a direct impact on the accuracy of the gear. Okay, so that's rolling. Now we can also mill or machine the gear teeth or the gear onto the shaft, or let me just rephrase, we can take a piece of raw material and machine the shaft and the gear from that same material. The photograph that you see here on the top right, that's now the final stages. So the shaft has already been cut with a different tool, and then that will typically be, or it will be, a turning operation, and then once that's done, the piece of material can be moved or transferred to a milling machine, and the individual teeth can then be the individual teeth can then be machined. Okay, so as with rolling, we get a high strength connection between the gear and the shaft. Okay, and it is a backlash free connection because it's the same piece of material. You will get good accuracy teeth, depending on the quality of the cutter and depending on the quality of the machine. This will influence then obviously the quality of the teeth. You also have relatively high costs associated with this technique because of the high volume of material removal that needs to happen. You can just looking at this photograph again, so the raw material that's actually shown here in the background will be slightly bigger than the gear. So all that material needs to be removed. Okay, if your application justifies it, then it is obviously a valid manufacturing and mounting technique. Okay, this is then also a photograph of a spur gear. So the question is, can it work then for a worm gear as well? And we have a nice video again that will show that it can in actual fact be done for a worm gear as well. Okay, so let me just quickly copy this link. Okay, there you can see the milling cutter in the background. This is a massive machine if you consider the amount of material that's removed. So very solid shaft, and there you can see the cutting process. Right, so then moving on to the next technique of mounting gears onto shafts. It is possible also to weld the gear on a shaft. This is just a photograph that I took from a video that I found on YouTube a year or two ago. And what happens is this shaft with the gear that is shrink fitted onto the shaft rotates, and this welding automated, I think it's an automated welding process, then lays down a weld joint between the gear and the shaft. Just going back to this first bullet point, so the gear is, as I said, it's press fitted, or the gear will be heated and it will be shrunk fit onto the shaft to get a very good fit, and then welding will secure it permanently further. You get good strength between the gear and the shaft. It's also backlash free connection between the gear and the shaft. I consider it to be less expensive than manufacturing the gear and shaft from the same piece of material. And I also found this bullet point on the internet. Welding is not very common because heating the gear and shaft can result in distortions that will cause the gear to either be noisy or fail prematurely. Okay, and then just going back to the previous techniques, the machining the gear and shaft from the same material, or this cold rolling. One of the disadvantages of this technique is when the gear gets damaged, the fact that it is made from the same material, and if the damage is severe enough to scrap the gear, then you have to replace that whole component. So another cost contributing factor that one should keep in mind. Okay. Now, I also a year or two ago on the internet got hold of this company, Dutton Linson. I hope I pronounce it correctly. They manufacture hand winches. And what they do, this you can see here on the image on the right hand side, is they use multiple laminated layers of stamped steel gear teeth. Now, I couldn't confirm this, but I think what happens here is these laminated gear teeth gets brazed together and onto the shaft. Okay, brazing is not as strong as welding, because there's no melting of the base material. There's a filler material that gets melted and then secures or cures between the two mother materials. And I think, as I said, this is what happens here. So, as we saw in the previous one, not very common. And you can also imagine for this application, accuracy is not a main consideration, neither backlash. So if there's a bit of inaccuracy or backlash, it won't hurt the application of a hand winch. Okay, so what this Dutton Linson's claims is that the manufacturing technique of using laminated layers of stamped steel provides greater strength than a single layer gear, and also helps to keep the manufacturing costs down. Right, so that's the second mounting technique. We looked at forming the gear and shaft from the same material. Then we looked at welding and brazing as a combined technique. And then the third technique is mounting the gears on a shaft using a clamp. Okay, and this company, Ringspan, they manufacture a vast array of products, one of which are clamps. Okay, and so let's just, I've given the website address, and I've also loaded the clamping element catalog on ClickUp, so it is available. And I just want to, from that clamping element catalog, just show two products two of the ring span clamping products that can specifically be used to clamp gears onto shafts. Okay, so the first one is what is called star discs. They are flat beveled rings that are slotted on the outside and inside. Now bevel, I hope you can see it from this image over here. It's a cone shape washer, if you like. So if this beveled spring lies flat on the table, then this edge over here, the inside edge, will be elevated. Okay, so it does not lie completely flat, and that is designed specifically like that, so that when an external axial actuating force is translated by the star disc into much higher radial force. To just rephrase that, so these blue arrows show it clearly. You can imagine if you have this thing lying on the table and you push it from above, what will happen is the outside will go a little bit further. It will translate radially, and the inside will also become a little bit smaller because it is actually being pushed down. So this, if you have a set of these star discs and you push it from externally and you obviously constrain it on the other side, it changes geometry to then push outwards and inwards, so it clamps onto the shaft and onto the gear. All right, now this force, this radial force indicated with the red arrows, creates a frictional connection between the star disc and the shaft as well as the hub. It is also a backlash-free connection. Now, this is an excellent solution in the sense that it ensures concentricity. It's very strong, backlash-free, and the fact that it is not permanent allows you to then, if the gear or the shaft gets damaged, you can replace the damaged component without having to replace both. So an excellent product to keep in mind. Okay, these two schematics just show the two different mounting options. If you have a shaft with a shoulder, then the star discs will be constrained against the shoulder, and as you tighten this nut, it will push the gear or whatever element it is that you want to mount to the shaft. It will push it axially, and that displacement, that axial displacement, causes the star discs to deform and secure the element onto the shaft, as I've explained on the previous slide. What's nice is that you can also adjust your design to clamp your element onto a continuous shaft. In other words, a shaft that does not have a shoulder. Okay, and this is an example of how you can do that. If you have a flange that sits onto the shaft, and your element itself has a shoulder, so as you tighten these bolts, there's axial movement of the flange that will deform the star discs and ensure a solid connection between the two elements. Alright, now the second ring span component that can very successfully be used to secure gears onto shafts is this so-called shrink disc, and the shrink disc is indicated with this different shades of red or pink. That's the shrink disc. It is a two-component mechanical device, and it also has nuts. Alright, so how it works is there's a taper between the light pink component and the dark pink component. So when you when you tighten the bolts through this hole that is sectioned on this view, the light pink component will be pulled, or the light pink component will be pushed forward and the dark pink component will be pulled backwards. So this slot will then ensure that this hollow shaft gets actually deformed to clamp onto the solid shaft. Okay, and there are also provision then for jacking screws. Okay, and this is shown in this section view here at the bottom. So if you want to undo the element, you will undo all the bolts and you will screw in the bolt in the jacking screw. And there you can see now the thread is in the light pink component of the shrink disc. And as you tighten the bolt, it will push the dark pink component forward and it will pull the light pink component backwards and disengaging this taper. And here's an example also from the Ringspan catalog. It's a backlash free connection, and this backlash free connection, so there's no backlash between the gear and the shaft. There will still be backlash between two adjacent gears. We're not talking about that backlash elimination. We're talking about eliminating backlash between the gear and the shaft. Okay, and this example is of a bevel spur gear onto a drive shaft of a gearbox with a specific shrink disc. So the Ringspan shrink disc is now indicated here with this dark shaded component. And what you have to note is that the bevel gear was specifically designed to give a thin walled sleeve that can be deformed with the shrink disc. Okay, if this sleeve was too thick, was a thick walled sleeve, then the shrink disc will not be able to exert enough force to clamp the bevel gear onto the shaft. So this is a specific design feature that was included in the design in order to use this shrink disc. Okay, so that was in clamping. So the next mounting technique is using keyways. Okay, and there are three types of keys that we can discuss. The first is a gip head key or a taper key. Okay, and avoid using such a key because they are difficult to remove. Okay, the Pratt and Whitney or parallel key, this is commonly used. Okay, and then there's also the Woodruff key. In my experience, this is something that is less common than the Woodruff key. Okay, and what you need to note here is the slot that is machined in the shaft has round ends on both sides, and that's because of the way that the slot is machined. It is machined from above with a round cutter that gets fed into the shaft. It gets pushed into the shaft, and as it rotates, it cuts away the material, it removes the material, and then once it's at the correct depth, this round cutter or end mill cutter is then controlled in the axial direction to the adequate length such that the key can actually then fit into that slot. Okay, so obviously if you have the key way on the end of a shaft, you will have only the one round end and an open end on the other side, as with this schematic of the gip head keyway. Okay, Now the Woodruff keyway, if you think about how that will be machined, so it will be a round cutter that will be controlled or moved into the material and then lifted again, and the cutter will have the same diameter as the key itself. Okay, so as I said, it's something that I haven't come across often, but I have seen this Pratt & Whitney or parallel key in a number of applications. Alright, so just in terms of how it is applied on gears, it is commonly used, as I said. There is backlash now between the connection of the gear and the shaft. There is backlash because you need a little bit of clearance between the key and this keyway. You can't make it perfect because then it will be impossible to get it in and even more difficult to get it out. Right, so you need clearance for such a mechanical mounting, and as a result of the clearance there will be backlash. Right, so I've also loaded the keyway sizes table on ClickUp. So this is the keyway size table, the top of the table. So how it works is the keyway depth and width of the keyway is standardized based on the diameter of the shaft. So if it's over 6 millimeters, the shaft diameter, up to and including 8 millimeters, you will use a 2x2 key, where 2 is the width and the other 2 is the height of the key. Okay, and then if you go to the right hand side of this table, it gives you the dimensions of the keyway plus the tolerances, both in the shaft as well as in the element that goes over the shaft, the element that you want to secure onto the shaft. Okay, so you're welcome to have a look at that table. Alright, so then the next method of securing, this is also taken from the hand winch manufacturer. So they have a non-round shape hole in the gear, okay, and they can obviously do this very elegantly with their lamination process. These gears will be stamped, and so your stamping die will have the adequate features in order to not only form the teeth of the gear, but also this square hole in the middle. Okay, and then you need to do the same for the shaft, okay, which is indicated over here. So accuracy, as I said, can be difficult with this technique because you need enough clearance, and here you've got 4 faces, so it will be a rattle fit. It will definitely not be a very high accuracy fit. And as a result of that, there will be backlash present in the connection between the shaft and the gear. Okay, now the next technique is talking about spring pin connection, and this is for low torque applications. Alright, so here is the URL to the manufacturing company from where I got this information. So one of the primary benefits of using a coiled spring pin, and maybe what I should do is just quickly show you what the spring pin looks like. So a spring pin is basically rolled from sheet metal, from spring steel sheet metal. Okay, so you get a light duty that's not rolled. Yeah, it's a thinner spring pin, and you get the heavy duty. And these pins are also available from Bozar. Okay, so then it's easy to understand from this schematic. What you have is you've got a hole that runs through the gear flange, or gear flange and the shaft, and that spring pin is then hammered into that hole. Okay, so, and that obviously then ensures that the gear, when the gear gets rotated, the shaft will rotate with the gear. One of the primary benefits of using a coiled spring pin to affix a hub or gear to a shaft is the coil pin's ability to prevent hole damage. Okay, that spring pin will get damaged before the shaft gets damaged. The hole in the shaft or the hole in the hub or gear. Another benefit is that the coil pin absorbs wider hole tolerances than any other press fit pin. Okay, and you can understand that it's the way it's designed. This pin can accommodate, or it can be forced into a smaller hole. It will just coil up a little bit more as it gets hammered or pressed into the smaller hole. Okay, now this translates to lower total manufacturing costs of the assembly. Okay, so because you can have a wider hole tolerances, you don't need that much of an accurate hole. The hole doesn't need to be reamed, for example, and it saves cost. But for low torque applications, okay, just take note of that. Now, countersinks on the holes are not recommended, okay, and that's shown here with this schematic representation on the right hand side. So it's the reason why it's not recommended will become clear a bit later on. In addition to countersinks not being recommended, the outer diameter of the shaft and the inner diameter of the collar should not be designed such that the distance between the shear planes exceeds 0.13 millimeters. Okay, so this is now the outer diameter of the shaft it's difficult to indicate it on this schematic representation, but basically that is now the I can show it here. Okay, so the outer diameter of the shaft, the difference between the outer diameter of the shaft and the inner diameter of the hub. Okay, so this hub will have a hole drilled all the way through, and the difference between those two diameters should not exceed 0.13 of a millimeter. Now, in both cases, what happens is the unsupported length of the pin in an area where torque may be applied is created. Okay, so that's what is shown in the schematic. Okay, so you can imagine now this is for a countersink. So if this right hand side blocks, these two right hand side blocks represent the hub of a gear, and the left hand side blocks represent the shaft. So if there's a torque being applied onto the gear that needs to be transmitted onto the shaft, this portion is unsupported, and that will cause bending moments which will shorten the lifespan of the spring. Okay, so there's bending moments, and it will be a cyclic loading which will yield fatigue damage to the spring pin. Okay, alright, so just some other guidelines. Installing a cylindrical pin into a hole on the surface of a cylindrical object leads to two-point contact between the pin and the hole. So this concentrates the compression force on only 2 points of the circumference, and what they suggest to avoid this is to make a flat surface on the shaft such that there's full circumferential contact. Now, a side note, obviously this can't be too deep, because then we are back at the previous slide where there's now a cyclic bending load on an exposed piece of the spring pin, which may lead to shorter life span. Okay, but for light torque applications, this can be a an elegant solution. Okay, we already looked at this slide, just the difference between light, standard and heavy duty spring pins, and you're welcome to visit Bozart to have a look at what they supply. Okay, then the last technique that for securing gears onto shafts that I would like to discuss is using a grub screw connection. This is typically for small and medium sized gears. As you can see in this photograph, a very tiny gear, and it's good practice to machine a flat on the shaft for the grub screw interface, because if you have just the round shaft and you tighten the grub screw, the end or the tip of the grub screw will cut and deform the shaft material, especially if the shaft is not hardened, and that may lead then to difficulty to remove the gear afterwards. But if you have, as on this slide, if there's a flat on the shaft and you tighten the grub screw onto that flat, if there's damage to this surface, it will not affect the ability of that shaft to be inserted or pulled out of the gear. Okay, and this was also a year or so ago. I did visit this Go Builder website again. They've got very nice products, a bit pricey, but very good quality, and it looks very nice. I've never touched any of their products, but it looks like a very nice range of products. Okay, so that's then, we quickly go back. Alright, so we looked at the different techniques of mounting a gear onto a shaft, manufacturing the gear and shaft from the same piece of material. There we looked at rolling and milling, welding or brazing the gear onto the shaft. We looked at the ring span elements for clamping a gear onto a shaft. We discussed keyways, and then the non-round shape of the hole in the gear and the shaft. We looked at that square hole and in the gear and the square shaft of the hand winch manufacturer. We discussed spring pins. I did not discuss a dowel pin, but the same principles really apply. The only difference is if you want to use a dowel pin or a shoulder bolt, as in our last practicum, you obviously need to have good accuracy but adequate clearance, such that the dowel can actually go through the hole. A spring pin is forgiving, it's a bit flexible, so if there's not perfect alignment, that spring pin will absorb that imperfection. A dowel pin is stronger, but it is a high precision and a very straight and cylindrical component, so you must have adequate clearance, not too much, but adequate clearance to ensure that the dowel will go into the hole. And then lastly, we quickly looked at grub screws for small and medium gears. So with that, I would like to thank you very much for listening. We've ended now with our gear topic. Our next topic will be rolling element bearings, and I look forward to that. Thank you very much.